you may have noted that we are approaching the end of the semester. And that's a sad thing, right? Because I'm going to miss all of you on Tuesdays and Thursdays. According to the schedule, we're meeting this week, Tuesday, Thursday, and I think the last official class is next Tuesday for graduate classes. I'm going to wait and see how it goes. I might, at no additional charge, have one more class on next Thursday, depending on how we cover the topics. But the end of the semester also brings to mind another wonderful experience that I know you're looking forward to, and that is the final exam of the course, always eagerly anticipated each year. And this class is small enough, I think we can have an oral final exam, which is even more fun than a written exam. So the question, two questions. First of all, which week should we do that? And then I will ask you to contact Michelle Thompson and arrange a time that's convenient. I think we can do it in an hour. I'll ask short questions that require long answers.
Finally, I think it was scheduled for the 6th, right?
6th of May.
So, yeah.
Now, so the question is, do we want to do it that week? What day of the week is the 6th?
It's a Saturday.
Well, we probably don't want to do it on Saturday. At least I don't want to do it on Saturday. But why don't we do it, shall we do it that week?
Yeah, the
Week preceding?
From the 1st to the 5th?
Yeah. And pick a time. Contact Michelle, and those who schedule their exam first get more of a choice, right? So it'll be sometime during that week. Now, let me think about that week. That's not going to work, actually, because I'm out of town most of the time. I'm in D.C. on the Tuesday, and I'm in Orlando on the Thursday and Friday. So how about the week before that? How about the week before that, right?
Maybe I'll just come to Orlando with you.
No, well, if I have a need for someone to help me there, I'll feel free to call on you. So what week is that, Kevin?
That's the 24th, 28th.
24th, 28th. I'm in town that week. That's a good thing. So shall we do that? Okay, so final exam. That'll be the week of April 24th to 28th. Is that right? And I will alert Michelle Thompson that you're going to contact her. And her email is mtomp@duke.edu. And she lives in, I think it's room 180. I think that's all right. 180 Hudson Hall. Okay, good. And today is the what? Today's the 11th? 11th. It says so on my paper if I can look. Very good. All right. Okay, so that gives you a couple of weeks to prepare, right? And then that'll be even better, right? Because then any other final exams you have will be the following week. Is that true?
Yeah. Yes.
Well, for those who have final exams. And if you don't, yeah, that's good. Okay, now, what else? Let me hand back your homework. I have some homework. Yelvin, how's that? How's my pronunciation?
Perfect.
Perfect. Ah, well, very good. Now, Kevin, you have the honor of having the official solution for this homework.
Right.
This is a high honor. It doesn't give you anything else other than an honor, but in fact, it requires more work on your part. You and Danny need to put this on the website for Sakai, right? Okay. Okay. Emilio, Adam, Charlie, Ty, Danny, and I think that's all I have. Okay. All right, good. let me tell you what I plan to do today, and maybe on Thursday as well. And then I'll ask for questions in case you have some. What we want to talk about is we want to talk more about transonic flow. And we want to think about three things. One is we want to think about how you start from, thank you. We're going to start from the nonlinear model and then go to a less nonlinear model, okay? And then that'll also take us eventually to linear theory, which, as we've discussed before, linear theory, either sometimes it just breaks down altogether, or more often it's just not as accurate in transonic flow as it is in subsonic and supersonic flow. So we want to do that. We want to talk about the distinction between what I'll call static and dynamic linearization versus just dynamic. The point here is that even in transonic flow, you can always do dynamic linearization and get a useful and meaningful result, even in transonic flow. But sometimes doing both static and dynamic linearization gets you into trouble. And then the last thing we want to talk about is something I'll call scaling analysis. And scaling analysis is a way to look at some set of equations which are hard to solve and decide, or in an order of magnitude sense, what the answer is without actually doing any computations to speak of. I mean, other than paper and pencil. And that's sort of a useful thing, right? And that's an idea that can be used in a wide variety of contexts, and we'll use it in the context of transonic potential flow theory. In fact, that's really the reason for doing all these things, because these ideas, I'm going to use these ideas to discuss transonic flow, which is a good example, but these ideas are used widely, in fact, not just in aeroelasticity. Of course, it's used more there because the people in aeroelasticity are pioneers. But it's used in a variety of contexts. Okay, but before we get into all of that, do you have any questions for Danny about the homework? Or I'll attempt to answer questions too. Or do you have any other questions about anything else, like what's on the final exam? I have no answers. I haven't decided yet. So,
when is the homework due?
When is it due? Friday. Yeah, I think that means you've got lots of time. Right?
Right in the final exam, you said short answers, short questions and long answers. I mean, you can be like, describe how we would solve the problem? Or...
Well, it's going to be more a test of concepts, I think, than detailed calculation. I mean, in an hour, you can't do a whole lot of calculations, right? So I might ask you, well, I'll give away a question, so I can't ask you this question. I might say, tell me what the distinction is between flutter and divergence, right? And then you would tell me, and then I would probe more deeply. The idea is you keep asking you questions until I find out what you don't know. Now,
That won't take long.
Well, in some cases it takes longer, in some cases it doesn't. But there's a technique to oral exams, and that is if someone asks you a question you know the answer to, you don't just blurt it out right away. You ponder it. Take as much time as you can because you know the answer, right? But see, I'm onto that. So anyway, okay. Anything else? But we're certainly you're not getting involved in. I might ask you. I probably will ask you to go to the board and I might write down an equation and ask you to tell me what it means or when it applies. Or I say now if you make the following assumption, what does that do to that equation? And So, but we're not going to do a lot of detailed calculations, right? But you might have to do a little mathematics. And above all, you might have to think. In principle, the purpose of the final exam is to educate you in two ways. First of all, you have to prepare for it. That's an education. And secondly, during the exam, you might learn something you didn't know you knew, or at least you were not consciously aware that you knew, but could have figured out for yourself had I not asked you the question. Does that help? Okay. Anything else? No. Okay. Then let's see. Let's start out with this nonlinear model leading to a less nonlinear model, and then leading eventually to a linear theory. If nothing else, I will expose you to the full glory of the nonlinear potential flow theory. So, nonlinear potential flow theory. First of all, let me remind you what it means to have a potential flow. It means that the velocity vector of the fluid, this q, is never to be confused with the generalized coordinate of the structure, right? So this is the velocity vector of the fluid. A potential flow is one where that is the gradient of some scalar called the velocity potential. And consistent, although strictly speaking not necessarily to be used, but almost invariably used in potential flow theory. We also assume that the processes are isentropic. And if you remember your thermodynamics, that means that P over rho to the gamma is a constant, where P is the pressure of the fluid, and rho, of course, is the density. It turns out to be convenient to define something in terms of pressure and density called the speed of sound, which has the physical interpretation of being the speed at which a disturbance in the fluid is propagated to other points in the fluid. And the formal definition of the speed of sound is actually the speed of sound squared, it's dp d rho. It's the derivative of pressure with respect to density. So let me see, I'll call that equation 1, equation 2, this is equation 3, okay? Now, I think you can probably differentiate this, right, if you put rho to gamma on the other side. And if you do that, you discover that it's gamma p over rho, okay? And at ambient conditions, the speed of sound is 343 meters per second. Now, we wanted to find the speed of sound for two reasons. One is it has that physical interpretation I just gave you. And the other is that in the context of nonlinear potential flow theory, you can express it entirely in terms of the velocity potential and the speed of sound, even in the nonlinear case. Okay. Remember, and this is in the book, and I'm peeling back one layer of the onion, but I'm not peeling all the layers. All right. You start out, when you derive the equations of fluid mechanics, you start out writing conservation of energy. Then you have balance of momentum, and then you have the thermodynamics, which is this isentropic law. Conservation of mass and this isentropic law are scalar, so we have two scalar equations. Balance of momentum, that's a vector equation. You know, F equals ma, that's a vector equation. So we have one vector equation, two scalars, But one vector equation is equal to three scalars in three dimensions, three spatial dimensions. So we have five scalar equations. We have five scalar unknowns, or if you will, two scalar unknowns, one vector. The vector unknown is q, but that in turn will be known in terms of the gradient of this scalar. The other two unknowns, of course, are p and rho. But it turns out you can manipulate the equations and reduce them entirely in terms of the loss potential and speed of sound. Okay? And I just happen to have a reliable reference here, which has those equations. So let me write those down for you. And again, this is the nonlinear potential flow theory. I'm going to write it this way for with malice intended, since I know where I'm going. You remember in linear theory we ended up with the Laplacian of phi, and then over here we had some terms divided by the speed of sound squared, right? And by the way, in the linear potential flow theory, that speed of sound was the free stream constant speed of sound, right? But this speed of sound obviously depends in general on the pressure and the density, and so if those are varying throughout the flow, so is the speed of sound. And the nonlinear theory takes that into account. So I want to take that 1 over a squared, and I want to put the a squared up here. And then the rest of it is something like the following. It's d dt of the gradient of phi dotted into itself. Plus a second derivative of phi with respect to time. We had a term like that in linear theory, right? In fact, as I've written this equation, this is a linear term. Not many linear terms in this equation, but that's one of them. Okay. Plus gradient of phi dotted into the gradient of del phi dot del phi over 2 equals 0. That's a scalar equation. The gradient of phi is a vector, right? It's the fluid velocity vector. But then you see how it appears. We've got all these dot products. When I take a dot product of vectors, I end up with a scalar, of course. And then here's a scalar. But then I take the gradient of that scalar, which gives me a vector. But then I take a dot product, and I'm back to the scalar again. So there are lots of vector terms in this scalar equation. The other equation is the following. Call this 4. A squared minus a sub infinity squared. This is the speed of sound far away from the airfoil. It's the ambient speed of sound. All of that divided by gamma minus 1. Equals I have to correct my own notes. Equals u infinity squared over 2 minus.
So then the other a is the speed of sound, the local speed of sound that we were finding.
Say again?
Is then that the local speed of sound?
This is the local speed of sound. This a is the local speed of sound. This is the free stream speed of sound. Okay? Yeah. And u infinity, of course, is the velocity at which the airfoil or wing or whatever is moving through the fluid. And then we have del phi dotted into del phi over 2. Okay? Now, the traditional approach is the following. We take phi and express it as u infinity x plus phi hat. And this is the perturbation, but it's a perturbation with respect to the free stream. And to see what this is physically, recall that q bar, that's equation 1, right? That's equation 1. Q bar is the gradient of phi, right? If I take the gradient of this thing, the gradient of this term is d phi dx times I bar, where I bar is the unit vector in the x direction, right? So this is u infinity times I bar. And then this is plus the gradient of phi hat, which is also a vector, right? So actually, you real strictly speaking, you start with this and integrate it once and get back to the velocity potential. But either way, it goes back and forth. Okay. Now, if we consistently linearize everything, we get the classical theory. But as we'll see, what happens in the classical theory is there's a cancellation of terms, right? Remember, there's a u infinity squared minus a infinity squared, and that's 0 when u infinity equals a infinity, and a term vanishes. That's a step too far when u infinity and a infinity are almost the same, when the Mach number is near 1. But nevertheless, let's proceed and see where we get from here. And the first thing I'm going to do is I'm going to take equation 7, or actually 6, and put it in 5 and see what happens. Okay? So let's do that. So let's put 7 and 5, and that will give us something, we hope. Well, I'm going to leave the left-hand side alone for a while, so that's still this. But now I've got u infinity squared over 2 minus d phi dt. Well, what is d phi dt? Well, d dt of this is 0, right? I mean, u infinity is a constant by the way we define it. So it's really just d phi hat dt. But then what about this? Well, gradient of phi, that's what this is, right? The q bar is the gradient of phi, so I need to take this and dot it into itself, right? And so what does that give us? Well, if I take this and dot it into itself, first of all, I get a u infinity squared, well, yeah, you can see that? I get a u infinity squared over 2. This is nicely going to cancel this, right? And then I get, what? I get plus 2 u infinity I dot del phi hat, right? Plus del phi hat dotted into itself. Ah, you can still see that. All right. Now I want to linearize. And
divided by 2.
Hmm?
Divided by 2.
Yeah, there's probably a 2 in there. Is that right? Yeah. Oh, yeah. In fact, this 2 is going to get canceled out by that 2, right? And this is also a 2, right? Oh, is that right?
Yes.
Yeah, that's right. Okay. All right. So this term is going to cancel that term. You agree with that? And then, I'm going to write that again at the top of the next page so we all see it. Then I have a squared minus a infinity squared over gamma minus 1 equals minus d phi hat dt minus u infinity I bar dot del phi hat minus del phi hat dotted into itself over 2. Okay? I guess we're up to equation 8 by now. Now, remember the whole idea is that the perturbation is in some sense small. And in particular, it's small compared to the free spring velocity, the gradient of the. So I'm inclined to throw that way as a higher order term. Okay. But these terms are linear, right? In classical, purely linear potential flow theory, I throw these away as well. Okay. And the reason I do that is because if you look at what a squared multiplies, it multiplies something involving phi in the phi equation, and therefore the Stuckey speed is going to give us these terms, which are linear in this equation, will produce nonlinearities in the phi equation. So in classical theory, I just throw these away too, and then I conclude a squared equals a infinity squared, and that's classical linear potential flow theory. But in the nonlinear theory, I need to retain this. Strictly speaking, I need to retain this, but there's an argument which justifies throwing it away, and that goes back to scaling analysis. I'll get to that later. But let's look at this term. It's minus u infinity I dotted into del phi. So what's del phi? It's partial of phi hat with respect to x times I, right? Plus partial of phi hat with respect to y times j, plus partial phi hat with respect to z times k, where I, j, and k are unit vectors in the x, y, z directions. But when I take the dot product, the only thing that survives is the I component of del phi, right? So this is really just equal to minus u infinity d phi hat dx. And that's the term we're going to retain in transide flow that we didn't retain when we looked at subsonic. Okay. Now, 3 or 4 pages of algebra later, okay, you do the similar thing in the phi equation, right? And when you do that, according to my analysis, you get something that looks like the following. Doing something similar. For the phi equation. That's 4 for those of you keeping score, right? That's this equation, right? In fact, here's where you can see why we, in classical fully linear theory, we throw away that term I'm now retaining. You see, if a squared depends on phi in some way at all, it gets multiplied by the Laplacian. That's a nonlinear term, right? That's a nonlinear term. So normally we throw away all nonlinear terms in the perturbation, but here we're going to retain it. And the reason we're going to retain it is when we do a similar perturbation analysis on the phi equation for perturbed, we're going to perturb this equation. Leads to the following. Don't have some pencils left. You end up with phi at xx multiplied by a squared infinity minus gamma minus 1. This is all a squared, right? This is all a squared, which I got from the equation I just talked about. And for the moment, I'm going to retain this term, even though I'm going to later try to justify throwing it away. Plus u infinity d phi hat dx minus u infinity squared minus 2 u infinity, u infinity d phi hat dx. Plus, the rest of the terms are pretty much what they were before. Times a squared infinity, sorry about that, plus v at zz a squared infinity. You see what I've done is that this first term, which was really a squared infinity, a squared times Laplacian, in these terms, I'm replacing a squared by a infinity. But in this one, I'm not, because there's a cancellation of terms due to the fact that these may be almost the same. And therefore, all these other terms which I normally throw away, I now am obligated to at least think about. Okay. And then it turns out the rest of the terms are pretty much the same as before, too. Minus ddt of u infinity dphi hat dx minus zero. Okay, so I'll call this 10. So all of these terms are actually, they're all linear, right? They all appear in the classical theory. In classical theory, we deleted that term, all those terms. We deleted that term, and we just had a squared minus u infinity squared, right? And of course, if we divided everything by a infinity squared, we'd end up with 1 minus u infinity over a infinity squared. That's the Mach number, right? And then we'd have, this would cancel out here, and then have all these terms multiplied by 1 over a infinity. So this reduces down to classical theory if I throw away this and I throw away that. But that's a step too far if this and this essentially cancel. Okay. So this is small perturbation theory, but it's not completely linear. In fact, because of this term and this term and this term, it's nonlinear. So doing a perturbation analysis, here's the principal moral of the story. Doing perturbation analysis doesn't necessarily lead to a linear model. Often one does perturbation with a malicious intent of creating a linear model, but sometimes, despite your best efforts, you can't get there. And transonic flow is one of those examples. Because two linear terms almost cancel, and therefore throwing away this altogether is a step too far, unless the gradients in x, this term, is small compared to this term and this term, which would be true if I had a very slender wing, right? If I had a very slender wing, it would be true, but certainly in two-dimensional flow, where this term vanishes, and all I would have would be this term, and of course these terms. Throwing away that term is too severe an approximation. Okay. Now, there's some further manipulations. Obviously, this term and this term can be combined. They're essentially the same kind of term, right? As I mentioned previously, you can often justify throwing away that term. In fact, let's look at that next, because that will allow us to talk about scaling analysis. How might I justify throwing away that term compared to that term?
Professor, the point of this is basically to determine whether or not the aircraft will fail, right?
Yes.
So if we've already determined that at like higher Mach numbers,
yeah,
it won't fail, is there any reason to believe that it would fail at lower speed?
Absolutely. Glad you asked that question. Let me draw you a picture. If I when I do a wind tunnel test, I often count the flutter boundary in terms of dynamic pressure versus Mach number. Okay, and there's a boundary. If this number is too high to give a Mach number, I flutter, and if it's low enough, I don't. So there's a boundary. And here's Mach 1. Here's how the boundary looks. Typically, it goes like this. The minimum is usually near Mach 1. Yeah. So often, even if you have a plane that flies supersonically, the most critical, or hypersonically for that matter, the most critical condition for flutter is near Mach 1. Because you got to get there, right? You got to go through Mach 1 to get to the higher Mach numbers. long as you're less than, I don't know, 0.7, if you're flying a Cessna 172, you certainly don't need to worry about transonic flow. But if you're flying an F-16 or F-15, or even 787, because the 787 gets almost up to Mach 0.9, and that's close enough to 1 that these effects become important. Yeah. And Murphy's Law, for those who know Murphy's Law. Murphy's Law says the theory is least reliable where you want it the most. Right? And that's certainly true in terms of aeroelasticity. The transonic aerodynamic models are least reliable, but that's where the most critical conditions most likely to occur. Yeah. And the other thing, which isn't said as often, the wind tunnels. I mean, sometimes people think that we test the wind tunnel must be the right answer. The wind tunnels are less reliable in transonic flow too, because they're, if you think about, there are these Mach lines that we talked about in the plane, but there are also Mach lines going up and down. And the Mach, remember how at Mach 1, the Mach lines, well, let me draw a picture. If I have a delta wing, so like this, now I'm at Mach 1.414, so I can draw them at 45 degrees. Remember, the Mach lines are going like this, but they're going up too, because the disturbances are propagating in all directions. So there are Mach lines going up normal to the surface of the wing. And if I'm testing the wind tunnel, they hit the wall. And if I'm near Mach 1, they're almost perpendicular. So they hit the wall and then they bounce back. If the Mach number is high enough, they hit the wall and they bounce back, but they don't hit the wing because the angle is acute enough that that's not a problem. So the wind tunnels aren't very reliable in transonic flow either. Don't tell NASA I said that, because they've got a very nice tunnel, and there's a lot of testing done in that tunnel, and it's a great source of pride to them, not to mention income. But there are problems in wind tunnel testing in Mach 1 as well as problems with the theory. Which is why some of us are still doing research on transonic flow. Okay. Okay. Oh, yeah. I was going to. I should have saved this for the final exam, but since I said I would do it, I'll do it. Remember, we had terms like this. We had a couple of terms like this. And I was asking you to tell me when I could throw that away. Okay. And one way would be to say, well, it's small compared to that. And if that were true, then I could throw this away. Right? Another, it might not be small compared to that, but then it might be small compared to something else I'm keeping. And then I could still be justified in throwing this away. So let's look at a couple of terms. We're going to compare. Okay, so compare these terms. But having some intent in mind, let me show some other terms. There's also a term that goes like this. Remember, this thing multiplies phi hat xx. And so I could also compare that to some other terms in my equation. For example, the term that goes like this: partial respective t of partial phi hat. Oops, I put the infinity in. G infinity partial phi hat respect to x. That's another term I'm retaining, right? So I'm asking is if I need to retain this term. And one way to justify throwing away is I could compare it to that. Another way would be to compare this term, because this term does get multiplied by this, to yet another term in the equation. Still with me? Okay. So the one way to do this comparison without actually, I mean, you could solve the problem and with or without the terms, right? But that kind of defeats the purpose. If you're going to solve the problem with the term in, you might as well just keep it, right? But use something called scaling analysis to justify throwing away this term compared to this term, or to justify throwing this term away when it gets multiplied with this compared to something else that also appears in a similar way in the equation. So how am I going to do that? This is such a good question. I'm sorry, I'm discussing. I have to think of something else. Well, we have to estimate the size of these terms somehow, right? Now, these two terms are both linear. Okay? So it can't, in some sense, depend on how big phi hat is, because phi hat appears as the first power in both cases. In this case, this is a linear term, right? And this is a nonlinear term because it involves a product of phi hats. Derivatives, to be sure, but a product of phi hats. Okay, so let's do that. Let's first of all look at this. Let's compare this to well, how big are those terms? Well, in my usual cavalier way, I'm inclined to look at sinusoidal motion. You allow me to do that? The advantage of doing that is that when I compute d phi hat dt, I know it's I omega phi bar e I omega t, which of course is just I omega times phi hat, right? So I know how big d phi hat dt is. It's just the frequency times phi hat. Okay. Well, what about d phi hat dx? How big would you like that to be? Well, phi varies, right, with x, but the scale of the variation is determined by the size of the object I have in the flow. And in particular, you might think it depends on the chord of the wing on the airfoil. Of course, a wing has multiple chords, right? So you have to pick some representative value. For an airfoil, it's just the chord. So I'm going to claim that this is roughly phi hat over c. It may not be exactly that. It might be twice that. It might be half that. It might even be 3 times that, or 1/3 of that. But it's not 1,000,000 times that, right? That's going to be the order of it. Okay. So now what are we going to do? When we compare this to this, I claim what I'm really comparing is omega. I'm just worried about magnitudes now. The I is magnitude of 1. I'm not worried about the phase shift. So this is omega times phi hat about, and this is u infinity times phi hat over c. Okay? Well, of course, they both are proportional to phi hat, so that doesn't tell us anything. But now it's clear that I want the frequency to be small enough. How small? Well, I want it to be small compared to that. Or if I prefer to rearrange things, I want omega c over u infinity to be sufficiently less than 1, right? That's our friend, the reduced frequency. So this term I can neglect if the reduced frequency is not too big, in particular if it's not of order 1. 0.1, probably. 0.2. If I'm desperate, maybe even 0.5, right? Depends on who I'm trying to justify this to and how much I really want to throw away that term, but you have to pick your number. Okay. Well, that's nice. What about if we want to compare, what were the other terms? Phi hat xx, d phi hat dt to u infinity cross derivative. Well, we can play the same game, right? let's try it. This is now phi hat squared, right? It's XX, so that's C squared. 1 times omega, so that's omega. Oh, I forgot to square that. Okay. And then over here, it's U infinity phi hat times omega because of d dt divided by C because of d dx. Okay. Okay. Well, there's an omega over C on both sides, so I'll cancel that. All right. There's a phi hat squared here and a phi hat here, so I can cancel one of those. So now I'm comparing phi hat over C to U infinity. All right? I think that's what I'm doing. Well, is that small compared to that? Well, yeah, that's why I assumed way back when, all right? I mean, I assumed that phi was U infinity times X, which is over C, plus phi hat, and when I was doing my perturbation, even though I was allowing for nonlinear terms, I was always assuming that phi hat was small compared to U infinity times C. So, consistent with what I started out with, I can ignore that term also. So even with nonlinear terms, if you're careful, sometimes you can ignore some of them, but not all of them, not in transonic flow. And so the classical small disturbance theory for transonic flow usually ignores that term as well. And by the way, this kind of reasoning works on structural equations. I assume, well, I just do structures and fluids. I think it probably works on electromagnetics and heat transfer and everything else. In fact, Professor Bijan, have any of you taken a course with Professor Bijan? He uses this method or something very similar to this method in heat transfer and thermodynamics. So I have a feeling that people have discovered and rediscovered this approach in many different fields. And it's very useful. For example, one more example that Kevin mentioned. I'm not going to go through this in detail, but just to point out that it does work in structural analysis as well. If I have a beam, right, we like beams, and I have a beam that is fixed at both ends. Using scaling analysis, you can show that the nonlinearity becomes important when the beam deflections become of the order of the thickness of this beam. On the other hand, if I have a beam that's fixed at one end and free at the other, one can show that the nonlinearities only become important when the deflections are in the order of the length of this beam, which is a much bigger number, right? And you see this in experiments, and you see it in the computations as well. Now, I have to confess that using scaling analysis to come to this conclusion was usually done after people had already done some computations and experiments. But once you know the answer, you can go back and reason. But scaling analysis would have told you that this would happen had you been sufficiently perceptive to do that. So lots of interesting things can be done there. Okay, let's see now. Oh, yes, I have one final topic. We have 20 minutes. Let me pause here for a moment. Okay, so what I'm trying to share with you is how you derive small perturbation, but yet still nonlinear equations. And then the question is going to be how we're going to solve them, which is what I'm going to talk about next. But let me pause here to see if there's any questions. And hopefully you're motivated to think that this would be relevant if you really wanted the airplane to not encounter flutter. Okay? All right. Okay. So what have we got here? We've got this set of nonlinear equations. Let me write it down in its final form. This is equation 10. Ignoring the term I've just described and collecting the other two terms, we end up with phi hat xx a infinity squared minus u infinity squared minus gamma plus 1 u infinity d phi hat dx. Remember, there were two terms, one of which had gamma minus 1, the other one just had 2, and therefore they combine, make the gamma minus 1 to gamma plus 1. And then we have phi hat yy phi hat zz minus whoops, 2 here. I think I left out a 2. Sorry about that. Okay, and then if you divide through by infinity squared, of course these go away, and this becomes 1 minus Mach number, etc. But this is still a nonlinear equation because of this product, right? So there are two ways to do this. One is to take the... I'm sorry? Oh, I'm sorry. Thank you. Yes, sorry about that. Okay. One way is to take Professor Howell's course on computational mechanics and learn how to use numerical methods to solve linear and nonlinear PDEs, right? And that's a good thing to do. Highly recommended. Another way is to do the following. And by the way, these are not mutually exclusive. You could do both. Another possibility is you could assume that phi hat, which is already a perturbation, can be further divided into a static part, which only depends on x, y, and z, and a dynamic part that depends on x, y, z, and also on t. Why would that be a useful thing to do? Well, it would be a useful thing to do because if I assume that I have an airfoil, even in transonic flow, and I allow it to oscillate, if that motion is small enough, there will be a non-trivial stack part because of the thickness of the airfoil, right? Now, there's an interesting question what happens if you actually have an infinitesimally thin airfoil. Remember, in linear theory, we separate the thickness effect and we separate the motion effect. In transonic flow, you really can't do that. If you have an airfoil that really has some shape, it's a NACA 12, and it's 12% thick compared to its chord, right? That thickness effect creates a non-trivial steady flow. We'll have shocks and all sorts of other interesting things at the Mach number near 1. Okay, so this static solution will not just be the free stream U infinity solution. It'll be something non-trivial, and it will be governed by this nonlinear equation with the time derivatives set to 0. Okay. Now, solving that nonlinear equation for static or steady flow is probably going to be a little easier than for dynamic flow. But the other thing that might happen is you might actually have measurements from steady flow, which would give you enough information about the static solution that you could use it then to do the dynamic problem. And how would we do that? We would take this equation, place it in here. Excuse me, this decomposition of the solution, this equation. Put it in here, determine the nonlinear equation that governs the static solution, and then we take the full solution, the full form of the solution in here, and linearize, really linearize in the dynamics. So then we would end up with a linear equation, but it'll have coefficients which depend on the static solution. Okay. Again, this is a very general technique. It's one that can be used in structural mechanics as well as fluid mechanics. But here in transonic flow, it's particularly useful. So I think I'm going to allow you to do that, but it's also in the book. So here's the idea. This is now equation 11, I believe. Still. Yeah. Okay. Place 11 and 10 and first determine the nonlinear governing equation for Vs, the static solution, right? Then put 11 and 10 and determine the linear equation for phi dynamic, ignoring all nonlinear terms in the dynamic. Now, what's the advantage of that? Well, I only need to solve that equation once for any kind of motion in terms of the amplitude. The amplitude of the motion will no longer matter, right? Because if I have a solution for one amplitude of motion, a linear theory will always tell me if I double the amplitude of motion, I'll double the pressure, I'll double the lift, I'll double everything on my airfoil or wing. And that's the solution I need to compute the flutter speed. Because by definition, flutter is a point of linear dynamic instability, right? So this kind of theory is often used in one or another of its forms to compute a flutter speed. It won't compute limit cycle oscillators, but it will compute flutter speeds. In fact, it will compute the same flutter speeds that a fully nonlinear theory would compute, because this is, by definition, it's the linear instability point that we call flutter. It's also, from a practical point of view, the point that's probably most dangerous and most interesting from the standpoint of survivability of the aircraft. So it's a useful mathematical approach, but it also has physical significance as well. Okay, and you're using Z-Aero, which is one of the Zona Technologies codes. They also have Z-Tran, and Z-Tran is essentially something like this. It first of all finds a nonlinear static solution and then uses that to infer a linear dynamic solution and uses that to compute the same kind of aerodynamic matrix that Z-Aero produces. Yes?
When you put these terms from 11 to 10, are you just putting the static and then at one time and then the dynamical?
Uh-huh.
Or do you put them both in and end up with the...
Well, you have to do this twice. First of all, you just put that in this equation, right? These terms will go to zero because, by definition, this doesn't depend on time. So I'll have a nonlinear equation. I'll have all these terms, right? And this term, but not these terms. And then I hope to solve that static solution. Okay, that's step one. Step two is now I take this whole thing and put it in here, And when I get to a term like this, in fact, I guess I have time to do that. When I get to a term like this, I linearize it in phi d. So, right, this product gives me the only nonlinear term, right? So the linear terms, I can always separate, because of superposition, all these other terms I can separate into static part and dynamic part. Are you with me? Yeah. So I only really need to worry about a term that looks like this, without all the coefficients. If I put phi static plus phi dynamic into this, right? I'll get phi hat xx phi s xx plus phi d xx times phi hat sx plus phi dx. Okay, and now what I'm going to do is I'm going to have a term like this, which also appears, of course, in the static equation. But then I'm going to have two other terms like this, one like this, plus another term that goes like phi dxx times phi sx. And then I'll also have a term like phi dxx times phi dx. So keep all of these on here, I suppose. But I'm going to throw that one away as being higher order. Okay. That's a nonlinear term in phi dynamic, and I'm not going to retain any nonlinear terms in phi dynamic. But I am going to retain this term because it's linear in phi dynamic, and I'm going to retain this term because it's linear in phi dynamic. This term I can make go away. How? Because once I have the static equation, I can subtract the static equation from the full equation, and all the terms that only involve statics will cancel out. But I'll be left with terms which are linear in phi dynamic, and in these cases have the static solution as coefficients. Yeah. So it's a linear equation, but not only the static solution appears as coefficients in the linear dynamic equation, and that makes it hard to solve. From a mathematical perspective, this is no longer a linear constant coefficient PDE, it's a linear variable coefficient PDE, unless those variations have certain special forms, like they produce Bessel's equation or something. I'm probably not going to be able to write down an analytical solution. Now, there are some severe approximations. There was a guy named John Sprider at Stanford who became famous by assuming that these coefficients, the static coefficients, were judiciously chosen constants. So he made it a constant coefficient equation. And you see there's one term here which involves phi dynamic XX, but that's kind of a term that also appears in the classical theory. But there's another term that is just phi d one derivative with respect to x. What that means is this equation, which transforms from elliptic to hyperbolic, depending on radial and subsonic to supersonic, because of that term, it has the ability to appear to be parabolic in the transonic regime. So it's a very severe approximation. The interesting thing about it is it actually can give you, at least qualitatively, interesting and valid results. But this has all been superseded by numerical procedures. One doesn't use Sprider's approximation anymore. But at the time, it was considered a great advance because he did this probably around 1960 or thereabouts, before computers were quite what they are today. Okay, I think I've told you everything I want to tell you about all those topics, unless there are other questions. No? No.
When I asked you that other question, you mentioned hypersonic.
Yes?
What is that?
Oh, hypersonic. That means the Mach number is really high. And there are two ways to define hypersonic. Some people would say, oh, if the Mach number is greater than 5, that's hypersonic. Okay? But a better way is MT is of order 1 or greater. Now, what is tau? I'm glad you asked. If it's a wedge, there are some. This is thank you. This is Z and this is X. There are some hypersonic vehicles that look like wedges. Tau is basically this angle. Okay, so the Mach number has to be high enough that m times this angle is of order 1. Okay, but you can also interpret it as m times alpha, where alpha is the angle of attack, because twist this, I'm also getting an angle with the relative flow. So m tau or m alpha order 1, which I think is a better definition, because what happens when that occurs, then some things that are important that potential flow theory just cannot handle. You have to go to a better approximation. Yeah. But often, commonly in literature, they'll say, well, this is faster than Mach 5, it must be hypersonic, but that's presuming that you have a shape that's like other shapes that people have looked at in the past. Okay. And there is quite a bit of work on hypersonic aeroelasticity at the moment. Now I'll just leave it at that. Okay. Other questions? Nope. Good. Well, we'll see you on Thursday.